Welcome back to Decentralized Application Development Crashcasts. I'm Sheila, and as always, I'm joined by my co-host, Victor. Before we dive in, I want to remind our listeners that if you're enjoying our content, please rate us on your podcast platform. It really helps us reach more developers like you.
That's right, Sheila. Your support means the world to us. Now let's get into today's exciting episode. We've reached a significant milestone. It's time for our Season 1 summary.
Absolutely, Victor. We've covered so much ground in our Introduction to Decentralized Systems season. But before we dive into our recap, I have a quiz question for our listeners. Are you ready?
I'm always ready for a good quiz, Sheila. Let's hear it.
All right, here goes. In the context of decentralized systems, which of the following is not a type of decentralization we discussed? A. Architectural, B. Political, C. Logical, or D. Temporal?
Ooh, that's an interesting question, Sheila. It really makes you think about the different aspects of decentralization we've covered. I like how it challenges our listeners to recall the specific types we discussed. Without giving away the answer, I think this question will help reinforce some key concepts from our season.
Exactly, Victor. Now, let's start our recap. Can you kick us off with a refresher on what decentralization actually means?
Certainly. At its core, decentralization is about distributing control, power, and decision-making away from a central authority. In the context of computer systems, it means creating networks where no single entity has complete control over the entire system.
That's a great explanation. I remember we talked about different types of decentralization. Could you remind our listeners about those?
Absolutely. We covered three main types: architectural, political, and logical decentralization. Architectural decentralization refers to how many physical computers a system has and how they're distributed. Political decentralization is about how many individuals or organizations control the system. And logical decentralization deals with whether the interface and data structures of the system appear more monolithic or divided.
Thanks for that breakdown, Victor. Now, let's move on to peer-to-peer, P2P networks. Can you explain what makes them special in the world of decentralized systems?
P2P networks are a cornerstone of many decentralized systems. Unlike traditional client-server models, in P2P networks, each node or peer can act as both a client and a server. This creates a network with increased resilience, as there's no single point of failure. It's like a potluck dinner where everyone brings a dish, rather than relying on one person to cater the entire event.
I love that analogy. Now, we also talked about something called distributed hash tables, or DHTs. Can you refresh our memory on what those are and why they're important?
Certainly, DHTs are a key technology in many P2P systems. They provide a way to store and retrieve data in a decentralized network efficiently. Imagine a huge library where books are distributed across many rooms, but there's a clever system that lets you quickly find any book you want. That's essentially what a DHT does for data in a P2P network.
That's a great explanation, Victor. Moving on to storage, we discussed decentralized storage systems. What are some key points our listeners should remember about those?
Decentralized storage systems are crucial for maintaining data in a distributed network. We talked about concepts like data replication, where multiple copies of data are stored across different nodes for redundancy and availability. We also covered consistency models, like strong consistency and eventual consistency, which deal with how and when data updates are propagated across the network.
Right, and I remember we mentioned IPFS as an example. Could you briefly remind us what that is?
Absolutely. IPFS, or Interplanetary File System, is a popular decentralized storage and sharing system. It uses content addressing to identify files, meaning files are retrieved based on what they contain, not where they're stored. This makes IPFS incredibly resilient and efficient for sharing large amounts of data across a decentralized network.
Thanks, Victor. Now, let's talk about networking in P2P systems. What were some of the key challenges and solutions we discussed?
Great question, Sheila. One of the main challenges in P2P networking is NAT traversal. Getting through firewalls and routers that might block direct connections between peers. We discussed techniques like stun, turn, and ice that help overcome these obstacles. We also covered peer discovery mechanisms, which help nodes find each other in a vast network.
Those are all great points, Victor. Now, before we wrap up, let's reveal the answer to our quiz question. The correct answer is D, temporal. We didn't discuss temporal decentralization as a type. We focused on architectural, political, and logical decentralization.
Excellent quiz, Sheila. It really helps reinforce the types of decentralization we covered. To summarize our season, we've journeyed through the fundamentals of decentralized systems. From the basic concepts of decentralization to the intricate workings of P2P networks, DHTs, decentralized storage, and networking challenges. These building blocks are crucial for anyone looking to develop decentralized applications.
Absolutely, Victor. We've laid a solid foundation for our listeners to build upon. As we close out this season, I want to remind our audience that we'd love to hear from you. Visit crashcasts.com, join our Discord community, or support us on Patreon. Your engagement helps us create better content for you.
And don't forget to subscribe to the podcast and rate us on your preferred platform. Your support means everything to us. We're excited to continue this journey with you in our upcoming seasons, where we'll dive even deeper into the world of decentralized application development.
That's right, Victor. Thank you all for listening, and we'll see you in the next season of Decentralized Application Development Crashcasts.